Hello, my name is Anja Brenner, and I would like to tell you something about the project Impact of Operator Interference in Dark Matter Direct Detection Experiments. Let's start simple, namely with the general motivation why physicists are interested in dark matter. The reason is simply that there is evidence for it, like in the rotation curves of galaxies or in the bullet cluster. As we can see in this diagram, there is roughly 5 times more dark matter in the universe than ordinary matter. Or in other words, there's a lot we do not yet understand. So it would be perfect if we detected dark matter particles, or if there is a null observation to constrain the properties of the dark matter particles at least. For the dark matter detection, there are different possibilities. There is particle production in the LHC, for example, or indirect detection, where we could check, for example, neutrinos coming from the sun with a specific energy range, which could have been produced via dark matter annihilations in the sun's core. The third possibility is direct detection. It is highlighted in blue because what I present today is applied to direct detection experiments. The overall idea of direct detection is quite easy. There is a detector located on the Earth, and dark matter particles from the galactic halo traverse the detector material. Here it might happen that a dark matter particle scatters off a target nucleus, and in the detector, it transfers the energy to that nucleus. The goal is to measure these recoils, which might be evidence for dark matter interactions. So far, dark matter wasn't detected, but at least the experiment can constrain and give us a limit on the dark matter nucleon scattering rate. And this is a quantity we can work with in order to get limits on the coupling strength between dark matter and nuclei, or in other words, the dark matter nucleon scattering cross-section. First, let me show you how to connect the experimental limit of the interaction rate with the dark matter nucleon scattering cross-section. For this, we consider a very simple example for the interaction Hamiltonian. Here we have 2 protons and 2 dark matter particles interacting. The interaction could be, for example, this one. There is an ingoing dark matter particle and an ingoing proton. Both scatter off each other, and the dark matter particle and the proton go out afterwards. In the interaction Hamiltonian, we have, in addition, Cp, which describes the interaction strength. Then we take the interaction rate R, which is proportional to the modulus squared of the matrix element. Plugging in the interaction Hamiltonian, we find that the interaction rate is proportional to the square of the coupling strength and a quantity we call R matrix. And this R matrix depends on the detector material, the dark matter velocity distribution, the local dark matter density, and the dark matter mass, which is all fixed by your model and by the choice of the detector. In addition, the experiment gives us the limit on R, so you can see that with this we can constrain the coupling strength. So what we obtain is such an exclusion plot with the coupling strength on the y-axis versus the dark matter mass. The limit that we obtain is this line, and since it is an upper limit, this red region above is excluded. Another quantity that describes the interaction between nuclei and dark matter is the cross-section, and one can easily convert one into the other, as one can see here. So also for the cross-section, we get such an exclusion plot. But of course, we have to keep in mind that those limits were obtained by assuming this interaction Hamiltonian. But the question might arise, what if other interactions are possible too? Here we assume that dark matter only couples to protons, but in general, dark matter couples to protons and neutrons. So to make this assumption a bit more general, we extend the interaction Hamiltonian from before by this part. So now we have the coupling between protons and dark matter and neutrons and dark matter. What does this mean for the limits on the coupling strength? Remember that in the simple case on the slide before, we found this expression. And since we now have protons and neutrons involved, this expression must be adapted. So instead of only CP, we have CP and CN. So for the coupling strength, we get a vector instead of a scalar. And accordingly, the R matrix is also not a scalar anymore, but a 2x2 matrix in this case. Now we already have a more general Hamiltonian, but it was found by Fitzpatrick and collaborators that dark matter may also interact through other interactions than this. So let's make the Hamiltonian even more general. We still have the two parts for CP and CN, but instead of the special interaction here and here, we write a general interaction operator. And it was found that there are 4 independent operators for spin 0 dark matter and 14 for spin 1/2 dark matter. That's why we have this sum here. With this new form of the interaction Hamiltonian, also the relation between the interaction rate R and the coupling strength has to be adapted. In general, it still leads to this expression, but for spin 0 dark matter, we get an 8x8 matrix, and for spin 1/2 dark matter, we get a 28x28 matrix. In order to get a bit more concrete, we can check what are the current limits of direct detection experiments, for example, xenon 1 ton and pico 60, which you can see here. In this plot, you can see the corresponding upper limit of the spin-independent cross-section versus the dark matter mass. And you can see the limits in blue for xenon and in green for pico. But the problem with this is that those collaborations typically assume that dark matter couples equally to protons and neutrons. But that is a very specific assumption. And here the question might arise, what happens if CP is not equal to CN? To understand this better, we consider a simplified example, meaning dark matter couples to protons and neutrons, but we only have one single operator and not the whole set of 4 or 14 operators. This means that the relation between the interaction rate and the couplings looks like that. So we have a 2x2 matrix here. And if we have a closer look, one can see that this has the form of a 2-dimensional ellipse. We use this fact to get a bit more insight. On the axis, we have CP and CN. And this is an example for such a 2-dimensional ellipse. In addition, I added the line which represents the parameter space that is allowed by assuming equal couplings between protons and neutrons. The parameter space that is still allowed by data is the blue area here, meaning that with the strong assumption, the upper limit is here. But here one can see very well that there is still some parameter space on the right of this strong limit assumption. This means that if one wants to be fully conservative, one should go to the very right of the parameter space. Here I have also related this interpretation of the ellipse with an exclusion plot. The red line is again the upper limit with the strong assumption, and the region above is excluded accordingly. If we consider this point in red here, or here, we can say that this is ruled out by the ellipse plot using the strong assumption, but actually it is still allowed by data. The most conservative upper limit is displayed here in green. The green cross we can see here or here is ruled out in a model-independent way, but the red cross could still be allowed. So what we learned from this finding is that one should be careful taking assumptions, because depending on the model, one might rule out too much parameter space. The final question here is, of course, how we get this conservative limit. And this is quite easy. It is this small analytic formula that only depends on the R matrix, which is fixed by your dark matter model and the choice of your detector, and the upper limit on the interaction rate, which is a simple input given from the experiment. On the following slide, I would like to show you how this affects the limits of xenon 1-ton and Pico-60. Remember, I have shown you this plot before. You can see the upper limits for a spin-independent cross-section with the assumption that Cp is equal to Cn. And on this slide, I also wanted to add the limits for the spin-dependent scattering cross-section versus dark matter mass. Also, assuming this fact that Cp is equal to Cn. If we now drop the assumption that Cp is equal to Cn, or in other words, if there can be interference among Cp and Cn, the limits get relaxed, as one can see very well here, by roughly 4 orders of magnitude, and similar for the spin-dependent cross-section. Remember that we assume for simplicity that we only have one operator to get this nice ellipse sketch. But actually, the interaction Hamiltonian for spin 1/2 dark matter could contain 14 operators. And taking this into account, the relaxation of the limits could be even more. So let's check that. Here again, the plots from two slides before. So now we also want to add a line where we take the interference between proton and neutron and all operators into account. And one can see that the limits get even more relaxed, slightly relaxed, but one can see some difference here. So the first thing one can learn here is that common assumptions might be too strong and models were ruled out, which are actually still valid by data. So far, you have seen limits provided from only one experiment at a time. But after that, we asked ourselves another follow-up question, namely if we can find something interesting if we combine experiments. And to answer this question, we check this ellipse plot. Again, we have the axis Cp and Cn, but now we have 2 ellipses, meaning 2 experiments. In green, we have experiment A, and in blue, we have experiment B. The most conservative upper limit for A is here, and for B, it is here. Naively, one could think that one simply takes the stronger limit of both, in this case, the one of B, but actually, the parameter space here and here is already ruled out by experiment B. And same for this parameter space here and here, it is ruled out by experiment A. And the parameter space that is still allowed by both experiments is this overlap region here. So the most conservative limit from the combination of experiments is therefore here. Also here we are interested how to obtain this value. Unfortunately, this simple analytic formula is not valid anymore, and we have to redo the calculation. For combining experiments, the result is not so short, but it is still solvable analytically, and it depends only on the R matrices of the experiments and on the corresponding number of observed events and the number of expected background events. So with this knowledge, we wanted to update these plots I have shown you already, and we added 3 more lines for the combination of experiments, which you can see here in red. And the biggest impact is probably visible on this right side. So check the conservative upper limits for the single experiment, which are here. And you can see that by the combination of the 2 experiments, we get stronger limits by roughly 4 orders of magnitude. But this limit is still fully conservative. And with this, I would like to summarize and conclude. So we learned that the common assumption that Cp is equal to Cn is quite strong. So we have developed a method to get the most conservative limits. Doing this, the limits can be relaxed by several orders of magnitude. And in addition, we have developed the method to get limits by combining experiments, which can lead to much stronger results, but being still fully conservative. And that's it from my side. Thanks a lot for watching my talk. And I'm looking forward to seeing you in the discussion session.